Okay, so in this section, we're going to take a look at what are the characteristics of a lipid and how they compare to the carbohydrates that we had just talked about. So as I had indicated, the carbohydrates are really good at being water soluble. They have lots of polar characteristics to it. The lipids are a collection of molecules that are hydrophobic. So they are, in many ways, they seem unrelated in other factors other than that insolubility in water. So these are hydrophobic molecules that we're going to be able to go through and pick out some critical characteristics of. Now, this is also a unique group because they don't technically form polymers. Now, there's definitely simpler components, but they don't follow the normal sequence. So, for example, in a sugar, mono plus mono gives you di. Disaccharides plus a bunch of monosaccharides, you get a polysaccharide. If you look at the situations where you're talking about proteins, you have amino acids, you have multiple amino acids sequenced in a particular order. So it's simple becoming more complex. The lipids follow a little bit of a different strategy, and I think a lot of that's just because it's a very diverse group. So they're not going to have a true monomer slash polymer configuration. All right. The unifying feature is the fact that there is little to no affinity for water, which is why they are classified as being hydrophobic molecules. And what we're going to see is that lipids are hydrophobic because they have mostly hydrocarbons built within them, and they're going to form those nonpolar covalent bonds. Now, there are sections within a lipid that have polar characteristics, but the overall structure of the molecule lends itself more so to being nonpolar. And in our body, probably the most, there's a lot of different areas we could point to, but our cell membrane is primarily lipids. It's phospholipid bilayer. So the way in which they orient themselves and how they influence what comes across the membrane or what's rejected going across the membrane is going to be pretty significant. So in this group, we have the fats, okay? And when we think of the fat category, we should be thinking energy molecules, something that we store, something we can metabolize and get energy out of. We have the phospholipids. Those are the ones that are building our membrane, okay? So we have a phospholipid bilayer, very critical. And then steroids, which in many ways are communication molecules in our body. So when you think about, I showed you in chapter 4, we were looking at the difference between, looking at a testosterone molecule. And we recognize those as being steroids as having those 4 fused carbon rings and being non-soluble in water, okay? So we can also throw waxes in that category. I don't have it listed on there, but there are definitely biological applications of waxes. So the first one that we have is a fat, and what we're going to find, and we've already talked about this back when we were discussing the orientation of different molecules, but we are going to have what's considered a fatty acid chain, and we're going to have a glycerol. So a glycerol is going to be the connection point, and you're going to have 3 fatty acid tails kind of coming off of it. So a lot of times when we look at this, they're going to be classified as a triglyceride because you're going to have 3 of those fatty acid chains hooked up to a glycerol, and they're going to be positioned in such that they're going to be attached onto those 3 different carbons where the alcohols are at, okay? So the fatty acid is going to have carboxyl at one end, followed by a long hydrocarbon chain. So we will put this together here for this next picture. We'll get a chance to look at that. But part of our recognition is being able to look at something and pick out some of the different functional groups. So I definitely have shown you, back in the carbohydrates, we saw the alcohol groups. We talked about the aldehyde versus the ketones. So let's look at this one right here. So this picture, this top image shows us an example of a fatty acid. And a fatty acid, you can see this part right here, the C double bonded to the O and the OH, that's called the carboxyl end. COOH. So like I said, it orients itself where you're going to have a double bonded carbon and you're going to have your OH at this point. This overall is polar, okay? But we've got all these things through here, this long chain, okay? These are hydrocarbons. This is absolutely nonpolar. So my molecule of glycerol, which is this part of the molecule over here, we have our 3 carbons with an alcohol group or a hydroxyl group attached there. So when you bring the carboxyl next to the alcohol, we get the same strategy that we saw with the sugars, and that is one of the hydrogens and an OH off of this are going to be released in the form of water, and they're going to form a bond, okay? This bond is called an ester linkage, okay? So whenever we are doing this, and because we're taking out water, this is a dehydration reaction, okay? So when it follows a similar pattern. So if you're taking something and you're removing water to make something more complex, it's going to be a dehydration reaction, and the bond that is formed right here is referred to as an ester linkage. So we can kind of go down this list and we can see that holding these things here. So this is a triglyceride, which is what fat would be. And I want to point something else out. Can somebody tell me why this is a fat and not an oil? Why is this picture depicting something that is classified as a fat and not an oil? What do we notice about the orientation? Yes, Devin. Okay. Let me ask you this next question. Is there a position for hydrogen in here? Anywhere else? Are there any other open spots for hydrogen to be added? And if I were to look at this diagram, I would probably say I don't see anywhere to put hydrogen in there. So if there's no extra room for hydrogen, we've classified this as being saturated. It's maxed out. There's no additional room for hydrogen. So this thing being saturated, that's a triglyceride. These tend to form very linear molecules. They tend to become packed together. So as a result of that, this is going to be a solid at room temperature. Okay? So it's telling us fats are going to stay separated from water because the water molecules form hydrogen bonds with each other, and fats are not able to be compatible with that. We also mentioned that a fat is going to be 3 fatty acids with a glycerol and an ester linkage, creating a triglyceride, or sometimes referred to as a triglycerol. All right. So as you kind of go through there and you look at the configuration and the orientation of that, when we look at how that matches up, we find that fatty acids, the length of them, there's going to be some variation. So you could have some carbon chains, they're going to be a little bit longer. The number of double bonds and the position of the double bonds is a point of variation. Whenever you have no double bonds, anything that's going to be without any double bonds, ran out of ink, sorry. No double bonds indicates that it's going to be saturated, and that's going to give you a molecule that's going to be linear, and it's going to pack together very tight, and it's going to give us a more rigid structure. The ones that are missing hydrogens are considered unsaturated. So whenever you are unsaturated, that's going to give it more flexibility, and that's going to give us the capability of seeing a molecule that is going to be a liquid at room temperature. So I'm going to stop at this point here. We'll go through and we'll finish up The lipids tomorrow, so I'm going to stop that. Not your group, the other, next time I meant.